Time is not the same for everyone. It never has been. Welcome to the Sleepy Lab. Tonight, we drift through one of the quietest revolutions in the history of science, the discovery that time itself bends, that it stretches and slows depending on where you are and how fast you move, and that traveling through time is not a dream. It has already happened. It is happening right now. If this is your first night here, consider subscribing. New episodes arrive each week, one sleepy soul at a time. Now, let's begin. Somewhere in a laboratory, a clock is ticking. Not quickly, not slowly, just steadily, as clocks do. But place that same clock on an aircraft, let it circle the Earth at cruising altitude, and when it lands, something will have changed. The clock will disagree with the one that stayed on the ground. Not by much. A handful of nanoseconds, perhaps. A sliver of time so small it barely has a name. And yet the difference is real, measurable, confirmed. Time travel into the future is not a theory waiting to be tested. It has already been tested. It has already happened in metal cases bolted inside aircraft, in the quiet hum of atomic clocks, counting oscillations of cesium atoms with almost unimaginable precision. The universe does not treat time as a fixed river, flowing at the same rate for everyone. It never did. To understand why, we have to go back to 1905. A young patent clerk in Bern, Switzerland, published a paper that would quietly dismantle the way humanity understood the cosmos. His name was Albert Einstein. The paper described what we now call special relativity, and buried within its mathematics was something almost impossible to accept at first, that time passes more slowly for objects moving at high speeds. Not as a metaphor, not as a feeling, as a physical fact. The faster something moves relative to an observer, the more slowly time passes for that moving thing. This relationship has a name, the Lorentz factor, and it describes precisely how much time slows depending on speed. At everyday velocities, the effect is so small it vanishes into the noise of ordinary life. But as speeds climb toward the speed of light, the effect becomes impossible to ignore. Consider what the numbers actually say. At 90% of the speed of light, a speed so vast that crossing the distance from Earth to the Moon would take barely more than a second, time for a traveler would pass at roughly 44% of the rate experienced by someone standing still. Less than half. For every hour that passes on the ground, the traveler experiences something closer to 26 minutes. Sit with that for a moment. And then consider 99% of the speed of light. At that velocity, the dilation factor reaches approximately 7. 1 year of travel would correspond to about 7 years back at rest. A traveler who left on a long journey and returned after what felt to them like a single year would come home to find that 7 years had passed for everyone they left behind. 7 years of seasons. 7 years of slow changes in the faces of people they loved. All while the traveler aged by 1. This is not a thought experiment designed to confuse. It is a description of how the universe actually works, and physicists have a name for the scenario that makes it most vivid: the twin paradox. Imagine two people born on the same day, identical in every way. One stays on Earth. The other boards a vessel capable of traveling at a significant fraction of the speed of light and sets out toward a distant star. Years pass on Earth, perhaps decades, and then the traveling twin returns. When they stand face to face again, something is different. The twin who traveled is younger, not slightly, meaningfully younger. Their body has aged less. Their cells have divided fewer times. Their heart has beaten fewer beats. The universe, in its quiet and indifferent way, has given them more future simply because they moved. It is called a paradox, because at first glance, it seems to create a contradiction. If motion is relative, if from the traveling twin's perspective, it is the Earth that moved away and returned, then why isn't the Earth-bound twin the younger one? Why isn't the situation perfectly symmetrical? The answer lies in something the traveling twin experienced that the other did not: acceleration. To leave Earth, the traveler had to speed up. To turn around at the distant star, they had to slow down and reverse. To return home, they had to decelerate again. These moments of acceleration, these changes in velocity, break the symmetry between the two twins. The traveling twins' journey through spacetime is genuinely different from the stationary twins, and that difference is written into their bodies when they meet again. The paradox, it turns out, is not a paradox at all. It is simply the universe being consistent, more consistent, in fact, than our intuitions are. There is something quietly profound about all of this. We tend to think of time as something external, a backdrop, a stage on which events occur, ticking forward at the same rate for everyone, everywhere, always. That is how time feels from the inside. It is how clocks on walls and watches on wrists seem to behave. It is the assumption baked into every calendar, every schedule, every appointment ever made. But that assumption is wrong. Or rather, it is an approximation, a very good one, at the speeds and scales of ordinary human life, but an approximation nonetheless. The deeper truth is that time is woven together with space into a single fabric, and that fabric responds to motion. It responds to speed. It stretches for things that move quickly and holds more firmly for things that are still. Every object in the universe traces its own path through this fabric, and along that path, time passes at its own rate. Your rate, right now, lying still, is not quite the same as the rate experienced by a particle accelerating through a detector somewhere, or a satellite tracing its arc above the clouds, or a muon born in the upper atmosphere and racing toward the ground at a significant fraction of the speed of light. Each of them is moving through time at their own pace. And so, in the most literal sense, are you? Time travel into the future is not waiting to be invented. It is already the nature of things. It is already written into the equations that describe every moving object in the cosmos. The aircraft clocks confirmed it. The mathematics of the Lorentz factor describes it precisely. The twin who travels returns younger, not because of any trick or illusion, but because the universe genuinely allowed them to spend less time getting to the same moment. That is where we begin tonight, with the quiet, confirmed, already measured fact that time is personal, that it bends around motion, that the future is not equally distant for everyone. Rest now. There is much more to come. The twin paradox has a name that suggests mystery, but the mystery dissolves quietly once you look at it closely. Two twins. One stays on Earth. One boards a vessel and travels at a significant fraction of the speed of light, then turns around and comes home. When they meet again, the traveling twin is younger. Not by much, at ordinary speeds, but at speeds approaching light by years. The question that troubled early readers of relativity was this: if motion is relative, why can't the traveling twin claim that it was the Earth that moved away and returned? Why isn't the situation perfectly symmetrical? And the answer is that it isn't symmetrical, not even close. The traveling twin had to accelerate, to leave, to turn around, to slow down and return. Acceleration is not relative in the same way that constant motion is. The traveling twin felt it. A force pressed them into their seat at departure. Another force turned them around at the far point of the journey. Another slowed them to a stop at home. The twin on Earth felt none of that. That asymmetry, the acceleration, is what breaks the apparent symmetry of the situation, and it is precisely what the mathematics predicts. The traveling twin genuinely, physically, measurably ages less, not as an illusion, not as a trick of perspective, as a real difference in elapsed time along two different paths through spacetime. This is not a paradox. It is a consequence. And it has been tested. In 1971, two physicists named Joseph Hafele and Richard Keating did something quietly remarkable. They took cesium atomic clocks, the most precise timekeepers available at the time, and they flew them around the world on commercial aircraft. Some flights went eastward, some went westward. A set of reference clocks stayed on the ground. When the airborne clocks returned and were compared to the ground clocks, the differences were exactly what relativity predicted, to within experimental error. The eastward flying clocks had lost time relative to the ground clocks. The westward flying clocks had gained time. The direction mattered because the Earth itself is rotating, and the aircraft flying eastward were moving faster relative to the center of the Earth than those flying westward. Speed affects time. Altitude affects time. Both effects were present, both were calculated in advance, and both were confirmed. It is worth sitting with that for a moment. Two men. Commercial flights. Atomic clocks and carry-on luggage, more or less. And the universe cooperated perfectly with the equations Einstein had written 66 years earlier. The differences were tiny, measured in nanoseconds. But they were real, and they were predicted, and they matched. That is what confirmation looks like in physics. Not a dramatic announcement, just numbers that agree. Now consider something you may have used today, or yesterday, or at some point in the recent past without thinking about it at all. A navigation system that tells you where you are on the surface of the Earth to within a few meters. GPS, the Global Positioning System, works by measuring the time it takes for signals to travel from satellites to a receiver. The satellites orbit at roughly 20,000 kilometers above the Earth's surface, moving at about 14,000 kilometers per hour. The system depends on extraordinarily precise timing. The clocks aboard those satellites must agree with clocks on the ground to within nanoseconds. But here's the problem. Or rather, here's where the universe insists on being taken seriously. Those satellites are moving fast. Special relativity says their clocks should tick more slowly than ground clocks, by about 7 microseconds per day, because of their speed. But those satellites are also far from Earth, sitting higher in the gravitational field, where gravity is weaker. General relativity says their clocks should tick faster than ground clocks, by about 45 microseconds per day, because of the reduced gravitational pull. The two effects work in opposite directions. When you combine them, the net result is that GPS satellite clocks run fast relative to ground clocks by roughly 38 microseconds per day. 38 microseconds. Sounds like nothing. But light travels about 11 kilometers in 38 microseconds, and GPS works by timing light speed signals. If those 38 microseconds were not corrected for every single day, the positional errors would accumulate. Within 24 hours, the system would be off by roughly 10 kilometers. 10 kilometers. That is the difference between arriving at your destination and arriving somewhere else entirely. The engineers who designed GPS knew this. They built the relativistic corrections directly into the system. The satellite clocks are deliberately set to run at a slightly different rate before launch, so that once they are in orbit, moving fast, sitting high in the gravitational field, they tick at the right rate relative to the ground. Every time a navigation system places you accurately on a map, it is, in a quiet and unannounced way, applying the physics of time dilation. Einstein's equations are running in the background of something millions of people use without a second thought. That is not a metaphor. That is engineering. And it brings us to the second great extension of time dilation, the one that took Einstein another 10 years to work out after special relativity. General relativity, published in 1915, revealed that gravity and time are not separate things. Gravity is not a force pulling objects together across empty space, as Newton described it. Gravity is the curvature of space-time itself, caused by the presence of mass and energy, and that curvature affects time. The closer you are to a massive object, the deeper you sit in its gravitational field, the more slowly your clock ticks relative to a clock farther away. This is gravitational time dilation, and it has been confirmed in laboratories, not just in orbit. Clocks on the ground floor of a building tick measurably more slowly than clocks on the top floor. The difference is extraordinarily small. The building would need to be very tall, and the clocks would need to be extraordinarily precise to measure it. But it is there. It has been measured. It matches the prediction. The ground floor sits deeper in Earth's gravitational field. Time there moves ever so slightly more slowly. You are lying down right now, which means you are, in the most technical sense, aging very slightly more slowly than someone standing upright whose head sits a little higher in the gravitational field than yours. The effect is immeasurably small at human scales, but it is not zero. And as you move toward more extreme gravitational environments, toward neutron stars, toward black holes, the effect grows from a whisper into something that reshapes the entire structure of time. Near the surface of a neutron star, where gravity is roughly 200 billion times stronger than on Earth, time dilation would be severe. A clock there would tick at a fraction of the rate of a clock in open space. An observer watching from a distance would see processes near that surface unfolding in slow motion, not because of any optical trick, but because time itself is moving differently there. And at the edge of a black hole, time, as seen from the outside, appears to stop entirely. But that is a story for a little further along. For now, let the simpler truth settle. Gravity slows time. Motion slows time. Both effects are real. Both are measured. Both are already woven into the technology of the world you live in. Time is not a constant. It never was. It only appeared to be because for most of human history, we had no clocks precise enough to notice the difference. Now we do. And the universe, it turns out, has been quietly bending time all along. Consider a building, an ordinary building, the kind you might pass without a second thought. Inside it, two atomic clocks are running. One sits on the ground floor. The other sits several floors above it. They started together, perfectly synchronized, ticking at the same rate. And yet, after enough time has passed, they will disagree. The clock on the upper floor will have ticked slightly faster. Not because it is a better clock, not because of any mechanical difference, but because it sits a little farther from the center of the Earth, where gravity's pull is ever so slightly weaker. And where gravity is weaker, time moves a little more freely. The difference is small, extraordinarily small. We're talking about fractions of a microsecond over the course of a day, but it is real, and it has been measured not just in tall buildings, but within the same laboratory, with clocks separated by nothing more than a meter of vertical distance. A single meter, and time runs differently at the top than at the bottom. This was confirmed with extraordinary precision in 2010, when physicists at the National Institute of Standards and Technology used aluminum ion clocks so sensitive they could detect the gravitational time dilation caused by lifting one clock just 33 centimeters, about the height of a large book, above the other. 33 centimeters of altitude, a measurable difference in the flow of time. There is something quietly profound in that. The floor beneath you and the ceiling above you are not moving through time at quite the same rate. The difference is too small to feel, too small to matter for any ordinary purpose. But it is there. The universe does not make exceptions, even for small distances, even for familiar places. Now carry that principle outward, away from buildings, away from Earth, toward objects where gravity is not a gentle background presence, but an overwhelming force. A neutron star is what remains after a massive star exhausts its fuel and collapses. What is left behind is a sphere perhaps 20 kilometers across, containing more mass than the Sun. The gravity at its surface is roughly 200 billion times stronger than what you feel lying in your bed right now. Near that surface, time dilation would not be a matter of microseconds or nanoseconds. It would be severe and strange. A clock resting on the surface of a neutron star would tick at a fraction of the rate of a clock floating in open space far away. An hour near that surface might correspond to considerably more time passing in the wider universe. The effect is not subtle there. It is structural. It reshapes what time means in that place. And yet, a neutron star is not the end of this story. Beyond neutron stars, there are objects where the collapse has continued further, where gravity has grown so extreme that not even light can escape. A black hole. The boundary of a black hole has a name: the event horizon. And the size of that boundary for a non-rotating black hole is described by something called the Schwarzschild radius, named for Carl Schwarzschild, who derived the solution in 1916, just months after Einstein published general relativity, while Schwarzschild was serving on the Eastern Front during the First World War. The Schwarzschild radius depends only on mass. For an object the mass of the Sun, it would be about 3 kilometers. For something more massive, the horizon grows. For something less massive, it shrinks. What defines it is simple. In principle, it is the distance from the center at which the escape velocity equals the speed of light. Inside that boundary, nothing, no matter, no signal, no information can travel outward. The interior is causally sealed from the rest of the universe. And at that boundary, something extraordinary happens to time. For an observer watching from a safe distance, far from the black hole, in relatively flat spacetime, a clock falling toward the event horizon appears to slow down. Not gradually and then stopping, but asymptotically. The infalling clock seems to tick more and more slowly as it approaches the horizon, its light growing redder and dimmer, its motion appearing to freeze. From the outside, the clock never quite reaches the horizon. It appears to hang there, suspended, as if time for it has simply stopped. This is not an illusion in any trivial sense. It reflects something real about the geometry of spacetime near a black hole. The gravitational time dilation becomes infinite at the event horizon. Time, as measured by a distant observer, does not merely slow there, it appears to cease. And yet, for the observer falling with that clock, for someone crossing the event horizon themselves, nothing unusual happens at that moment. Their own clock continues ticking. They feel no jolt, no boundary, no signal that they have crossed into a region from which there is no return. The event horizon is not a wall. It is not a surface you could touch or see. It is a threshold defined entirely by what is possible, by the geometry of paths through spacetime. An infalling observer would cross it without ceremony. They would continue to experience time passing normally, at least for a while. The strangeness that awaits them lies not at the horizon, but deeper inside, near the singularity at the center, a place where the known equations of physics break down entirely, where our current understanding reaches its edge and goes quiet. But at the horizon itself, from the inside, there is nothing to mark the crossing. Only afterward, looking outward, would the traveler notice something different, the entire future of the outside universe? In a sense, compressed into the light still able to reach them. The universe outside would appear to speed up. Time out there would seem to race forward. Two perspectives on the same moment. From outside, the clock freezes at the horizon, suspended forever in the last light it could send outward. From inside, the clock crosses without pause, carrying its traveler into a region where the future leads only inward. Both descriptions are consistent with the mathematics. Both are, in their own frame of reference, correct. This is not a contradiction. It is what spacetime geometry actually looks like when gravity becomes extreme enough to bend not just light, but the very structure of before and after. There is a stillness in thinking about this. Somewhere in the universe, there are black holes millions or billions of times more massive than the Sun. Their event horizons are vast, so vast that the tidal forces at the horizon would be gentle enough that a traveler might cross without being torn apart. They would simply pass through into a region of space-time from which no return is possible, without any single dramatic moment to mark the transition. Time, in those places, does not behave the way it does here. It does not flow evenly in all directions. Near enough to the horizon, the future points inward. There is no path that leads back out, not because of any force pushing you inward, but because inward is simply where all futures go. The geometry of time itself becomes the trap. Let that settle for a moment. The same equations that explain why your GPS works, why atomic clocks on aircraft tick differently than those on the ground, why a clock on the top floor of a building runs fractionally faster than one on the ground floor. Those same equations, followed to their natural conclusion, describe a place where time as we experience it loses its familiar shape entirely. The universe contains such places. They are not hypothetical. They are out there, in the dark between galaxies, bending space-time around them in silence. And the physics that describes them is the same physics that governs the quiet room where you are resting now. And that same physics, followed not outward to the edge of a black hole, but inward, down through the layers of the earth beneath you, reveals something quieter and somehow just as strange. The core of this planet is older than its surface. Not by much, in the way we usually count years, but by a real and measurable amount, roughly 2.5 years, accumulated over the lifetime of the Earth. The rock at the center of the world has experienced slightly less time than the rock beneath your feet, because it sits deeper in a gravitational field, and deeper means slower, and slower means less time has passed. 2.5 years of difference, written into the geometry of the planet itself. And it does not stop there. The Sun, 93 million miles away, is massive enough to curve space-time across the entire inner solar system. Its gravitational field reaches Earth and slows every clock here, yours, the one on your wall, the atomic clocks in laboratories, relative to what those clocks would read if they were drifting alone in empty space, far from any mass at all. Not by much. The difference is small, but it is real, and it has been measured, and it means that simply existing near a star is enough to alter the rate at which time passes for you. We are all, always, moving through a universe that is not neutral about time. To understand why, it helps to step back and see the larger shape of things. In 1905, Einstein showed that space and time are not separate. They are woven together into a single fabric, a fabric with 4 dimensions, 3 of space, 1 of time, and the name for this fabric is spacetime. 2 years later, a mathematician named Hermann Minkowski took Einstein's equations and gave them a precise geometric form. He showed that space-time is not just a useful metaphor, it is a genuine mathematical structure with its own rules of distance and angle and curvature. Minkowski once said that space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union is space-time, and within it, there is a quantity called the space-time interval. The interval between two events, two moments, two locations, combines their separation in space and their separation in time into a single number. And that number is the same for every observer, regardless of how fast they are moving, regardless of where they are. This is what makes space-time more than just a convenient way of talking. The interval is invariant. It does not change. While two observers might disagree about how far apart two events are in space, or how far apart they are in time, they will always agree on the interval that combines both. There is something deeply restful in that idea. In a universe where so much depends on perspective, on motion, on where you happen to be standing, there is still something that holds still. Something that every observer, everywhere, measures the same way. The interval is that thing. Every object that exists traces a path through space-time. Not just through space, through space-time. Every position, at every moment, laid out as a continuous line through 4 dimensions. This path is called a world line. Right now, as you lie still, your world line is moving through time even though you are not moving through space. You are traveling through time at the only speed available to you. 1 second per second, always forward, never pausing. Light moves differently. A photon, a particle of light, also traces a world line through space-time. But its world line has a quality unlike anything with mass. The space-time interval along a photon's path is exactly 0. Not nearly 0. Not approximately 0. Precisely, always 0. This means that from light's perspective, if we can even speak of such a thing, no time passes at all. A photon born in the heart of a distant star and absorbed by your eye after traveling for thousands of years has, in some sense, experienced no journey whatsoever, no duration, no waiting. The emission and the absorption are, for the photon, the same moment. That is what it means to travel along a null geodesic, the name physicists give to the path light follows through space-time. Null, because the interval is nothing, 0, a path through the universe that takes no time at all. And yet here we are, with mass, with weight, with the slow accumulation of moments, unable to reach that speed, unable even to approach it without time itself beginning to stretch around us. There is a reason for that limit, a deep one. As an object with mass accelerates, it takes more and more energy to push it faster, not because of friction, not because of any mechanical resistance, but because of the geometry of space-time itself. The closer you get to the speed of light, the more energy is required for each additional increment of speed. The curve rises steeply, then more steeply, then approaches vertical. You would need infinite energy to reach it, and infinite energy does not exist. So the speed of light is not simply a rule someone wrote down. It is a horizon built into the structure of reality, the boundary where the geometry of space-time closes off. And woven into that boundary is something else, something quieter. Causality. If anything could travel faster than light, it could, in certain reference frames, arrive before it departed. Effect before cause. A signal sent and received before it was sent. The speed of light is not just a speed limit. It is the lock on the door between cause and effect, between the past and the future, between what can influence what. Remove it, and the orderly sequence of events, the thing that makes the universe legible, that makes memory possible, that makes you the person who fell asleep tonight rather than some scrambled collection of moments in no particular order, begins to dissolve. So the universe holds the line. Now, there is a way of thinking about all of this, about world lines, about space-time, about the fixed geometry of intervals that leads somewhere very still and very strange. If every event in your life traces a world line through four-dimensional space-time, if the interval between any two events is fixed and invariant, then in some sense, all of those events already exist. Not sequentially, not one after another, but simultaneously as coordinates in a structure that simply is. This is called the block universe. In the block universe, the past has not gone anywhere. The future has not yet arrived. Both are simply there, laid out like a landscape you might view from above, every moment present at once, every event occupying its fixed location in four dimensions. Your childhood exists in the block universe. The moment you first learned to read, the first time you felt cold air on your face in winter, these are not memories of things that vanished. They're coordinates. They're still there, in the geometry of space-time, as real as the moment you are lying in right now. And the future, whatever it holds, is also already there, fixed. Waiting not in the sense of anticipating, but in the sense of simply existing at coordinates you have not yet reached along your world line. In this view, the flow of time, the sense that now is moving, that the present is a special place, that yesterday is gone and tomorrow is coming, is not a feature of the universe itself. It is something that arises in consciousness, a kind of motion through a structure that does not itself move. The universe, in the block view, is not a process. It is a thing, a static, four-dimensional object, complete and whole, containing every moment that has ever been or ever will be. That is a thought worth sitting with quietly. Einstein himself sat with it, and he found it troubling. He wrote, near the end of his life, that the distinction between past, present, and future is a stubborn illusion. He used that word, stubborn, as if the illusion refused to yield even when he knew better, even when the mathematics told him clearly that the present moment had no special status in the equations. He found no comfort in the block universe. He found it cold. He grieved for the passage of time, even as his own work suggested that passage might be something the mind imposes rather than something the universe provides. There is something quietly moving about that. The man who more than anyone else revealed the geometry of time, unsettled by what he found there. And the unsettling goes deeper still. Because the block universe is not just a philosophical position, it is suggested by something measurable, something that falls directly out of special relativity. Two observers moving relative to each other will not agree on whether two distant events happened at the same time. This is called the relativity of simultaneity, and it is not a matter of signal delays or imprecise clocks. It is a fundamental feature of space-time geometry. Two events that are simultaneous for one observer, happening at the same moment in their frame of reference, will be separated in time for an observer moving relative to them. One event will appear to have happened first, the other second, and a third observer, moving in the opposite direction, might see them in the reverse order. None of these observers is wrong. None of their clocks is broken. They are simply moving through space-time along different world lines. And the geometry of space-time means they slice through it differently, each one's present moment cutting across the four-dimensional structure at a slightly different angle. This means there is no universal now. There is no single moment that is the present for everyone, everywhere. what is happening right now. For you, lying still in this room, that now is yours. It belongs to your world line, your frame of reference, your particular path through space-time. Someone moving relative to you, even at ordinary speeds, has a now that is tilted slightly differently. For events far enough away, their now might include things that are, for you, already past or not yet arrived. The present is not a universal fact, it is a local one. And if there is no universal present, then the division of the universe into past, present, and future, the division that feels so absolute, so obvious, so simply true, is not written into the fabric of things. It is written into the perspective of the observer. All of this, the invariant interval, the world line, the block universe, the relativity of simultaneity, points toward a picture of time that is very different from the one we carry in our bodies. The felt sense of time moving, of now being now, of the past being gone. These are real experiences. They are not mistakes. But they may be the way a conscious mind moves through a structure that does not itself move. And then there is one more shape that space-time can, in theory, take. A path that does not go forward. A path that curves. And curves. And returns. A closed timelike curve is a world line that loops back to its own beginning. A path through space-time that, if you followed it long enough, would bring you back to the same event you started from, the same place, the same time, the same moment. Not a metaphor, a solution to the equations. Kurt Gödel was a mathematician, not a physicist. And yet, in 1949, he handed Einstein a solution to his own equations that Einstein found deeply unsettling. Gödel asked a simple question. What if the universe itself were rotating? What would space-time look like then? He worked through the mathematics carefully, and what he found was a universe that was perfectly consistent with general relativity. Every equation balanced, every condition satisfied, and yet inside that universe, closed time-like curves ran everywhere, not in some exotic corner, not near a special object, everywhere. In Gödel's rotating universe, if you traveled far enough in the right direction, you would eventually arrive back at the moment you left, not a place you had been, the moment, the same point in time. Einstein received the paper as a birthday gift. He called it disturbing. The Gödel universe does not appear to be our universe. Our universe shows no evidence of rotating as a whole. The large-scale structure of the cosmos, the way galaxies are distributed, the way the cosmic microwave background is patterned, points to a universe that is on the grandest scales, not spinning. So Gödel's solution remains what it has always been, a proof that the equations permit this, a demonstration that closed time-like curves are not forbidden by the mathematics of general relativity, only, perhaps, by the particular universe we happen to inhabit. And yet the equations keep offering these shapes. In 1963, a New Zealand mathematician named Roy Kerr found another solution, this one describing a black hole that rotates. A spinning black hole is different from a simple, non-rotating one in ways that matter deeply. It does not just curve space-time around it, it drags space-time with it, the way a spoon dragged through honey pulls the honey along. And deep inside a Kerr black hole, past the outer event horizon, past the second inner boundary called the Cauchy horizon, the mathematics reveals something familiar. Closed time-like curves. Again, whether those curves are physically real, whether anything could survive the journey to that region, whether the Cauchy horizon itself is stable, these are open questions. Many physicists believe the inner structure of a rotating black hole would be far more violent than the clean mathematics suggests. that quantum effects would tear apart any orderly geometry long before a traveler reached those curves. But the solution exists. The shape is there, written in the equations. Rotation keeps appearing in these stories. There is something about spinning, about matter or space-time turning, that seems to create the conditions where time can fold back on itself. Which brings us to one of the stranger theoretical constructions in all of physics: a Tipler cylinder. The idea is this: take a cylinder of extraordinarily dense matter, denser than a neutron star, and set it spinning very rapidly along its long axis. General relativity predicts that such an object would drag the space-time around it into a kind of spiral. And if the cylinder were long enough, and dense enough, and spinning fast enough, the dragging would become so severe that the spiral would close. World lines near the cylinder would curve not just through space, but back through time. A path that began at one moment could, by traveling around the cylinder in the right way, return to an earlier moment. Frank Tipler worked this out carefully in 1974. He showed that the mathematics was consistent, that such a cylinder, if it were infinitely long, would genuinely produce closed timelike curves in the space around it. But he also showed the limits of the idea. A finite cylinder, one with ends, one that could actually exist, would not produce the same effect. The closed timelike curves would not form, unless the cylinder were made of something that does not exist in any known form. Matter with negative energy density. Matter that pushes outward where ordinary matter pulls inward. So the Tipler cylinder joins a growing list of structures that are permitted by the equations that are internally consistent and that require something the universe does not seem to readily provide. There is a quietness to all of this. Each of these solutions, Gödel's rotating cosmos, Kerr's spinning black hole, Tipler's infinite cylinder, arrives at the same threshold and stops. The mathematics opens a door. The physics of the actual universe seems to keep it closed. And then there is the wormhole. A traversable wormhole is, in its simplest description, a tunnel. Not a tunnel through rock or earth, but a tunnel through space-time itself, a shortcut connecting two regions that might otherwise be separated by vast distances or by time. The idea has roots in the earliest days of general relativity. Einstein and Nathan Rosen described a kind of bridge between two regions of space-time in 1935. Though their version was not traversable, nothing could pass through it without being destroyed. The traversable wormhole came later, shaped more carefully. The picture is something like this. Imagine space-time not as a flat sheet, but as something that can be folded. Two points that appear far apart on the surface might, if the sheet were folded, be very close together through the interior. A wormhole would be a passage through that interior, a throat connecting two mouths, each opening into a different region of space. And if one mouth of the wormhole were in a different gravitational field than the other, or if one mouth had been accelerated while the other remained still, then the two ends would have aged differently. Time would have passed at different rates at each mouth, and a traveler passing through the wormhole from the younger mouth to the older one would arrive not just in a different place, but at an earlier time. The wormhole, in this way, could become a path into the past. General relativity does not forbid this. The equations permit wormhole geometries, but they come with a condition that is, in its own way, as strange as anything else in this story. To hold a wormhole open, to keep the throat from collapsing under its own gravity before anything could pass through, would require matter with negative energy density. Matter that, in a sense, pushes outward rather than pulling inward. Matter that has less than nothing. This is not ordinary matter. It is not any matter we have ever held or measured in bulk. And yet it is not entirely fictional either. There is a phenomenon in quantum physics, a quiet, subtle effect that hints at something like negative energy existing in the real world, in small and carefully constrained ways. The vacuum of space, it turns out, is not empty. Even in a region containing no particles, no light, no matter of any kind, quantum field theory says that something is always happening. Fields that permeate all of space are never entirely still. They fluctuate, constantly, at every point. Tiny ripples of energy appearing and vanishing. Too brief and too small to observe directly, but real in their effects. These are called vacuum fluctuations, and they're not hypothetical. Their consequences have been measured. When two metal plates are placed very close together in a vacuum, the fluctuations between them are restricted. Only certain wavelengths fit in the narrow gap, while the fluctuations outside the plates are unrestricted. This imbalance creates a pressure. The plates are pushed together by the difference between the vacuum inside and the vacuum outside, a force arising from nothing, from the structure of empty space itself. This is the Casimir effect. First predicted in 1948, first measured convincingly in the 1990s. A real, repeatable, laboratory observation of the vacuum doing something. The energy between the plates, in this configuration, is in a certain sense lower than the energy of ordinary empty space, which is as close as the real world has come to demonstrating negative energy density. It is a very small effect. The amounts involved are immeasurably far from what a traversable wormhole would require, but the principle is there, quiet and strange, in the gap between two plates in a laboratory somewhere. And so the gap between two plates becomes a kind of threshold. On one side of that threshold, a small, measurable, laboratory effect. On the other side, the open question of whether spacetime itself could be shaped by something similar. A traversable wormhole, a tunnel through the fabric of space and time, is not forbidden by general relativity. The equations permit it. They permit many things. But permission in mathematics does not mean ease in practice. A wormhole of that kind would need to be held open, and holding it open would require matter with negative energy density, not just low energy, negative. A region where the energy of space is less than the energy of ordinary empty space. The Casimir effect shows that such a condition can exist in a very small way, in a very controlled way, between two plates, in a laboratory, for a fleeting geometry of restricted wavelengths. But the amounts involved are vanishingly small. The gap between what the Casimir effect produces and what a stable wormhole would require is not a gap of degree. It is closer to a gap of kind. The wormhole would need negative energy threaded through a macroscopic tunnel, sustained, structured, held in precise configuration. Nothing in our current understanding of physics suggests a path from here to there. And yet the question was asked seriously. In 1988, the physicist Kip Thorne and his colleagues published a paper that treated traversable wormholes not as fantasy, but as a problem in physics. They asked what conditions would be necessary, what the geometry would look like, what exotic matter would need to do. And in the course of that work, they noticed something. If a wormhole could be made traversable, and if one of its mouths were then accelerated to high speed, or placed deep in a gravitational field, time dilation would cause the two mouths to age differently. One mouth would tick more slowly than the other, and because the interior of the wormhole connects them directly, a traveler passing through might emerge not just in a different place, but at a different time. The wormhole would become a time machine, not through any additional mechanism, not through any new physics, simply through the combination of a traversable tunnel and the time dilation that relativity already predicts. This was not presented as a blueprint, it was presented as a consequence. If the first step were possible, if exotic matter could hold the wormhole open, then the rest would follow from equations that have been tested and confirmed for over a century. The paper was careful, it was precise, and it was deeply unsettling to some, because it suggested that the laws of physics, as currently written, do not obviously forbid a machine for traveling into the past. Stephen Hawking found this troubling. Not emotionally troubling, in the way a person might find a dark thought troubling, but troubling in the way a physicist finds an inconsistency troubling, as a sign that something is not yet understood. In 1992, Hawking proposed what he called the chronology protection conjecture. The word conjecture is important. It is not a theorem. It is not a proven result. It is a reasoned suspicion, offered with the weight of physical intuition behind it, but without a complete proof. The conjecture holds that the laws of physics conspire, that is the word Hawking used, quietly, to prevent the formation of closed timelike curves, to prevent any region of spacetime from looping back on itself in a way that would allow travel into the past. The mechanism he pointed to was quantum fluctuations near any region of spacetime that was beginning to form a closed timelike curve near any nascent time machine. Virtual particles would trace the loop. They would travel the curve, return to their starting point, and travel it again and again. Each pass would add to the energy of the fluctuations. The energy would not dissipate. It would accumulate, growing without bound as the loop tightened. Before the time machine could be used, before the first traveler could step through, the quantum vacuum itself would flood the region with unbounded energy, destroying the structure that made the loop possible. The universe, in this picture, does not forbid time machines through a single clean law. It prevents them through a kind of self-correcting instability, a feedback that erases the possibility before it can be realized. Hawking offered this with characteristic dryness, noting that the conjecture was supported by the fact that we have not been invaded by tourists from the future. There is something almost gentle in that observation, the absence of visitors as evidence, the silence of history as a kind of data. But the conjecture remains unproven. The full calculation requires a theory of quantum gravity, a framework that unites general relativity and quantum mechanics, and that theory does not yet exist in complete form. So the chronology protection conjecture stands as a strong suspicion, not a certainty. A door that may be locked, but whose lock has not yet been fully examined. And in the meantime, the questions remain. The oldest of them is not really about physics at all. It is about logic. The grandfather paradox has been posed in various forms for as long as people have seriously imagined backward time travel. In its simplest version, a traveler goes back in time and, through some action, prevents their own grandfather from having children, which means the traveler was never born, which means the traveler never made the journey, which means the grandfather was never prevented, which means the traveler was born after all. The loop has no consistent resolution. Each step undoes the one before it. It is not a paradox in the sense of a surprising result. It is a paradox in the older sense, a statement that cannot be true and cannot be false without contradiction, a place where ordinary logic breaks down. Some physicists treat this as decisive. If backward time travel leads to logical contradictions, then backward time travel is impossible, regardless of what the equations seem to permit. The universe does not allow contradictions. Therefore, it does not allow this. Others are less certain. They note that the paradox assumes a single, linear timeline, one history that must remain consistent with itself. But that assumption may not be the only possibility. There are frameworks in which the paradox dissolves, not because the contradiction is resolved, but because the structure of time is different from what the paradox assumes. Those frameworks carry their own questions, their own strangeness. But for now, The grandfather paradox sits at the center of the problem, like a quiet knot, a place where the physics of curved spacetime meets the logic of cause and effect, and neither one gives way easily. The universe permits so much. It permits time to slow near a massive body. It permits clocks to disagree. It permits the geometry of spacetime to curve and fold in ways that seem, from the outside, almost impossible. And yet something, whether it is the chronology protection conjecture, or the instability of exotic matter, or the simple weight of logical consistency, seems to hold the past in place. Unreachable. Not because the universe is simple, but because it is, in some deep way, careful. There is another paradox worth resting with for a moment. Not the grandfather paradox, with its violence and its severed lineage. This one is quieter. It is called the bootstrap paradox, and it concerns not destruction, but origin. Imagine a book about the mathematics of time travel, filled with equations no one has ever derived. A traveler from the future brings this book back to the past and gives it to a young physicist. That physicist studies it, builds on it, and eventually the work becomes the foundation of the very time travel technology that sends the traveler back in the first place. The book exists. It is real. It can be held and read and copied. And yet no one ever wrote it. It arrived from the future, which was built on its contents, which arrived from the future. There is no origin, no first moment when the knowledge was created. It simply loops, endlessly, each instance of the book coming from a version of itself that came from another version of itself. The bootstrap paradox does not destroy anything. It does not erase a grandfather or unravel a family line. It simply removes the beginning. It asks where something came from, and the answer is nowhere. It always was, because it always will have been. This is a different kind of strangeness. Not a contradiction, exactly. More like a gap in the fabric of causality, a place where the chain of cause and effect folds back on itself and swallows its own tail. Some physicists find this deeply troubling. Others find it merely strange. A few find it almost beautiful in its self-containment. Igor Novikov, a Russian physicist, looked at these loops and paradoxes and proposed something elegant. He called it the self-consistency principle. The idea is this: any event that occurs through time travel must be consistent with the history that already exists, not because some force prevents inconsistency, but because inconsistency is simply not a possible outcome. In Novikov's framework, a time traveler could move through the past. They could walk its streets, breathe its air, touch its walls. But they could only ever do the things that already happened. If history records that a stranger appeared in a village in 1887 and left without speaking to anyone, then a time traveler who visits that village in 1887 will be that stranger. They will leave without speaking to anyone. Not because they are forced to, but because that is what occurred. The past is not a place that can be changed. It is a place that has already been. There is something almost peaceful in this view. The traveler is not constrained by chains or barriers. They are simply part of a story that is already complete. Every choice they make in the past is a choice that was always going to be made. Their presence there is not an intrusion. It is a thread that was always woven in. And yet, the question of free will sits at the edge of this framework like a shadow. If a traveler can only do what already happened, in what sense are they choosing anything at all? They move through the past with the full experience of agency, the feeling of deciding, of acting, of being present, and yet every action is predetermined by the consistency of history itself. Novikov's principle does not answer this. It simply holds that whatever the traveler does, it will have been consistent. The paradox is not resolved so much as ruled out by definition. Not everyone finds this satisfying. And so there is another framework, one that approaches the problem from a different direction entirely. The many-worlds interpretation of quantum mechanics was proposed in the 1950s as a way of understanding what happens when a quantum system is measured. In the standard picture, measurement causes a wave function to collapse, all the possible outcomes reduced to one. In the many-worlds view, they do not collapse. Every outcome occurs. The universe branches quietly and completely into versions of itself, where each possibility is realized. This interpretation, if taken seriously, offers a different resolution to the paradoxes of time travel. In the branching model, traveling backward in time does not mean returning to your own past. It means entering a branch, a parallel history that diverges from your own at the moment of your arrival. The world you step into is not the world you came from. It is a world that was, until that moment, identical to yours. But your presence changes it, and from that point, it becomes something else. The grandfather paradox dissolves here. Not because the contradiction is resolved within a single timeline, but because there is no single timeline to be consistent with. The traveler who goes back and prevents their grandfather from having children does not erase themselves. They simply enter a branch where they were never born. Their own origin timeline, the one they departed from, remains intact. They came from somewhere. They arrived somewhere else. The bootstrap paradox also softens in this view. The book that loops through time may loop through a series of branches, each one receiving it from the last. The origin is still absent, but the loop is not perfectly closed. It spirals, slightly, through adjacent histories. This is a more permissive universe, one in which the past is not a fixed and unreachable country, but a branching structure of possibilities, each one real in its own way. And yet the many-worlds interpretation carries its own weight of strangeness. It requires that every quantum event, every particle interaction, every measurement, every moment of observation splits the universe into new versions of itself. The number of branches is not merely large, it is, in any meaningful sense, beyond counting. All of them real. All of them proceeding in silence, unknown to each other. Whether this is a feature or a cost depends on what you find more troubling. A universe that forbids paradox by fiat, or a universe that resolves it by multiplication. Both frameworks are serious. Both are held by serious people. Neither has been confirmed by experiment, because the experiments that would distinguish them have not yet been designed, and may never be. And so, the paradoxes remain open, not as failures of understanding, but as honest markers of how far the questions reach. There is one more thread to follow before leaving the territory of paradox. It concerns not the direction a traveler might move through time, but the direction time itself moves. Time, as we experience it, flows forward. The past is fixed. The future is open. Causes precede effects. A broken cup does not reassemble. A memory is of something that has already occurred, never of something that has not yet happened. This feels so obvious that it barely seems worth saying. And yet, when physicists write down the fundamental laws of nature, the equations that govern how particles move, how forces act, how fields evolve, almost none of those equations distinguish between forward and backward in time. Run the mathematics in reverse, and the laws still hold. A film of two particles colliding and bouncing apart looks equally valid whether played forward or backward. The universe, at its most fundamental level, does not seem to care which direction time runs. And yet, here we are, experiencing only one direction. always forward, always away from the past and toward what has not yet happened. This is one of the deepest unresolved questions in all of physics. Not why time travel is difficult, but why time has a direction at all. The answer, as far as we can tell, begins with disorder. There is a principle in physics, one of the few that does seem to point in a direction, called the second law of thermodynamics. It states, in its simplest form, that the total disorder of a closed system tends to increase over time. Things spread out, they mix, they lose their arrangement. A drop of ink released into still water does not gather itself back into a drop. It diffuses, slowly, irreversibly, into the whole. This tendency toward disorder has a name: entropy. Entropy is not quite the same as messiness, though that image is close enough to rest with, more precisely, it is a measure of how many different microscopic arrangements could produce the same large-scale appearance. A glass of water in which all the fast molecules happen to be on one side and all the slow ones on the other is possible, but it is extraordinarily unlikely. There are vastly more arrangements in which fast and slow molecules are scattered throughout, so that is almost always what you find. High entropy states are simply more probable, not because nature prefers them in any deep sense, but because there are so many more of them. And this is where time enters. When you watch a film of a broken cup reassembling itself from shards on the floor, leaping upward, sealing its cracks, landing whole in a waiting hand, you know immediately that the film is running backward. Not because any fundamental law of physics forbids the reassembly, but because the probability of all those fragments moving in precisely the right directions at precisely the right moments is so vanishingly small that it has never been observed, and almost certainly never will be. The forward direction of time, in this view, is simply the direction in which entropy increases, the direction in which arrangements become more probable, the direction in which ink spreads, cups break, and memories accumulate. But this raises a quiet and rather unsettling question. If high entropy states are so much more probable than low ones, why was the universe ever in a low entropy state at all? The answer reaches back to the very beginning. The early universe, in the first moments after what we call the Big Bang, was in a state of extraordinary, almost incomprehensible order. Not order in the sense of neatness or arrangement as we usually picture it, but order in the thermodynamic sense. The matter and energy of the cosmos were compressed into a configuration with an almost unimaginably small number of possible microscopic arrangements. It was, in the language of entropy, a very special state. And everything since then has been a slow unfolding away from that state. Every fire that burns, every star that shines, every thought that forms and fades, all of it is the universe moving from that initial low entropy condition toward the vast, diffuse, high entropy future that awaits it. The arrow of time is not written into the laws of physics at the microscopic level. It is written into the initial conditions of the universe itself. We experience time as flowing forward because we are downstream from a very particular beginning. This is a strange thing to sit with. The reason you remember yesterday and not tomorrow. The reason causes come before effects. The reason you are aging rather than growing younger. All of it traces back, in some deep sense, to the state of the cosmos 14 billion years ago. And yet, even this does not fully close the question. Because while entropy gives us the arrow of time in our everyday experience, in the world of cups and ink and memory, the fundamental equations of physics remain, at their deepest level, almost entirely symmetric in time. Almost. There is a small crack in that symmetry, a quiet exception that physicists discovered not through philosophy, but through careful observation of certain subatomic particles, kaons and mesons. These are particles that exist only briefly, produced in high-energy collisions and decaying within fractions of a second. They're not part of ordinary matter. You will never encounter one in daily life. But in the 1960s, and again in later decades with greater precision, physicists noticed something unusual about the way they decay. The decay of these particles is not perfectly symmetric in time. If you were to run the process in reverse, mathematically, in the equations, the result would not be identical to the forward process. There is a subtle but measurable difference, a slight preference for one direction over the other. This is called CP violation, a term that refers to a combined asymmetry between matter and antimatter, and between a process and its mirror image. It is small, delicate, easy to miss, but it is real, and it has been confirmed by multiple independent experiments. What it means is that the universe, at some level, does have a built-in preference, not a strong one, not one that shapes the everyday flow of time in any obvious way, but a preference nonetheless, a whisper of asymmetry in the otherwise symmetric laws of nature. And this whisper may carry enormous consequences. One of the enduring puzzles of cosmology is why the universe contains matter at all. In the earliest moments after the Big Bang, matter and antimatter should have been created in equal amounts. When matter and antimatter meet, they annihilate each other, converting entirely into energy. If the universe had begun in perfect symmetry, all the matter and all the antimatter would have destroyed each other, leaving nothing but light. And yet, here we are, made of matter, living on a planet of matter, in a galaxy of matter, in a universe where matter, for reasons not yet fully understood, won out. The CP violation observed in kaons and mesons suggests that the laws of physics treat matter and antimatter slightly differently, that there is a small but decisive imbalance built into the fabric of things. And it is this imbalance, this tiny asymmetry, that may be responsible for the fact that anything exists at all. The universe we inhabit, the stars, the planets, the quiet weight of your body resting now may be the residue of an ancient asymmetry, a slight excess of matter over antimatter in the first moments of time. Everything else annihilated, and what remained was everything. It is a humbling thought to carry toward sleep, that the direction of time, the existence of matter, the fact of your own presence here, all of it may trace back to a subtle crack in a symmetry that most of the universe's laws still honor. Physics does not yet have a complete explanation for CP violation. The standard model of particle physics predicts it, but only partially. The observed asymmetry between matter and antimatter in the universe is larger than current theory fully accounts for. Something remains to be understood. And so the arrow of time points forward not because the laws of physics demand it at every level, but because the universe began in a particular way, and because hidden within its deepest symmetries, there is a small, quiet preference that tilts everything, just slightly, in one direction. Forward. Always forward. Into higher entropy, into greater disorder, into the open and unmapped future. You are part of that unfolding. Every breath, every heartbeat, every slow drift towards sleep is the universe moving, gently and irreversibly, away from its beginning. And there is something restful in that. To be carried forward not by effort, but by the nature of things themselves, by the shape of time, by the quiet, ancient tilt of the cosmos. Let it carry you now. And yet, even that quiet tilt, that thermodynamic preference for disorder, is not the only asymmetry time carries. There is another one, smaller, stranger, and harder to hold in the mind. It lives inside the act of observation itself. In quantum mechanics, a particle does not have a definite position, or a definite speed, or a definite state, until something measures it. Until then, it exists as a spread of possibilities, a wave function, a kind of probabilistic cloud hovering between outcomes. And then, measurement happens. The cloud collapses. One outcome is selected, the others vanish. This is called wave function collapse, and it appears, as far as anyone can tell, to be irreversible. You cannot uncollapse a wave function. You cannot restore the possibilities that were lost. The measurement has happened, and the universe has moved on. This is a different kind of arrow. Not thermodynamic, not about entropy spreading through a room, but something more intimate. Something that happens at the smallest scale every time the world is observed. Whether wave function collapse is a real physical process or an artifact of how we describe quantum systems is still genuinely debated. Physicists have not agreed on this for nearly a century, and that uncertainty is worth sitting with quietly. The nature of measurement, of what it means for something to become real, remains one of the deepest open questions in all of physics. What is less debated is the strangeness of what follows from it. Some physicists have begun to wonder whether time itself, the very thing we have been tracing through this whole long night, is not fundamental at all. Not a backdrop, not a river, not even a fabric, but something that emerges, the way temperature emerges from the motion of countless molecules, the way wetness emerges from water, a property that appears at a certain scale, woven together from something deeper. The something deeper, in this case, may be entanglement. Quantum entanglement is the phenomenon by which two particles, once connected, share a common quantum state regardless of the distance between them. Measuring one instantly affects what can be known about the other, not through any signal, not through any force, but through a correlation written into the structure of the wave function itself. Some physicists, working at the edge of what current theory can say, have proposed that time as we experience it may arise from the entanglement between quantum systems, that what we call the flow of time is, at bottom, the way entangled systems register change in each other. A clock ticks not because time passes, but because it is entangled with the rest of the universe, and that entanglement evolves. This is a quiet and radical idea. It has not been proven. It may not be provable with current tools, but it points towards something worth resting in. That time may not be given to the universe from outside. It may be something the universe generates from within. There is an equation that sits at the heart of this question. It is called the Wheeler-DeWitt equation. It was developed in the 1960s as an attempt to bring quantum mechanics and general relativity together to describe the quantum state of the entire universe. And when you write it down, time disappears. Not approximately, not in some limit. The equation contains no time variable at all. The universe, described at this deepest level, appears to be static, a timeless wave function with no before and no after. This is deeply strange, because we are clearly here, and time is clearly passing, or at least appears to be. The equation does not say time is impossible. It says time may not be written into the foundations. It may be something that emerges when you look at one part of the universe from the perspective of another part. Carlo Rovelli, one of the architects of loop quantum gravity, has spent much of his career thinking carefully about this. His view is that time is relational. It does not exist as an absolute backdrop against which things happen. It exists only as a comparison between changing things. A clock does not measure time. It is time. in the only sense that matters: change measured against change. In this picture, there is no universal now. There is no master clock ticking somewhere behind the scenes. There is only the web of relationships between things that change and the patterns those relationships trace. It is a view that ancient philosophers would have recognized, even if the mathematics would have been foreign to them. Time as relation, not substance. Time as the shape of change, not the container it happens in. Let that settle for a moment. All of this, and we have not yet left the neighborhood of the familiar, because general relativity has one more thing to say about time, something more concrete, more measurable, and in its own way, just as strange. Space-time, as Einstein described it, is not merely curved by mass, it can also be dragged. A rotating object, a planet, a star, a black hole, does not simply sit inside space-time and warp it. It pulls space-time around with it as it turns the way a spinning ball submerged in thick honey would drag the honey along in slow spirals. This is called frame dragging, and near a rapidly rotating black hole, the effect becomes extreme. Space-time itself is swept around the rotation axis. An object near such a black hole would be carried along, not by any force acting on it, but by the motion of the space-time it inhabits. Time, in that region, is not merely slowed. It is twisted, redirected, pulled into the spin. Frame dragging is not a theoretical curiosity. It has been measured here, around the Earth. Our planet rotates, and as it does, it drags the space-time around it ever so slightly. The effect is tiny, almost unimaginably small at the scale of everyday life, but it is real, and it has been confirmed. A satellite called Gravity Probe B was launched in 2004, carrying 4 of the most perfectly spherical objects ever made by human hands: gyroscopes, polished to within 40 atoms of a perfect sphere. As the satellite orbited, those gyroscopes were monitored with extraordinary precision. And over the course of the mission, they precessed. Their axis drifted, not because of any mechanical imperfection, but because the space-time they were moving through was itself slowly rotating, dragged by the turning Earth beneath them. The measurement matched the predictions of general relativity. Frame dragging is real. The Earth is, in the most literal sense, stirring the fabric of space and time around it as it turns. And so we arrive at a picture of time that is almost nothing like the one we began with. Not a fixed current, not a universal backdrop, not Evie, perhaps a fundamental ingredient of reality. Time bends near mass. It slows near gravity. It stretches with speed. It may be dragged by rotation. It may emerge from entanglement. It may not exist at the deepest level of the equations at all. And yet here it is, passing, as it always seems to, carrying you forward, gently, without effort on your part. The breath slowing, the thoughts growing softer at their edges, the body settling into the particular stillness that comes just before sleep. Whatever time is at its foundation, relation, emergence, geometry, illusion, it is doing something right now, something quiet and reliable, moving you as it moves everything, away from one moment and into the next. Let it. There is one more thread to follow before the night grows fully quiet. A thread that reaches back to the very first moments of the universe. When the cosmos was young, unimaginably young, a fraction of a second old, it was also unimaginably hot. And in that heat, the fundamental forces of nature were unified, pressed together into a single seamless thing. As the universe cooled, those forces separated, crystallized, the way water crystallizes into ice when the temperature drops below a certain point. And when water freezes quickly, it does not always freeze evenly. Cracks form, boundaries between regions that crystallized in slightly different ways, lines where the structure of the ice does not quite match on either side. Something similar may have happened in the early universe. As the forces separated, the fabric of space-time may have developed its own cracks, its own boundaries, one-dimensional threads of concentrated energy, thinner than a proton, stretched across the cosmos. We call them cosmic strings. Not strings in the sense of something soft or woven, but defects, seams in the structure of space itself, places where the old unified state of the universe was, in a sense, preserved, trapped inside a filament of extraordinary density. A single cosmic string, if it exists, would weigh roughly 10 million billion tons per centimeter of its length. It would have no thickness to speak of, and it would stretch, in principle, across the entire observable universe, or loop back on itself in a closed ring. And here is where time enters the picture again. In 1991, a physicist named J. Richard Gott worked through the mathematics of what would happen if two cosmic strings passed near each other, moving in opposite directions at high speed. The geometry of space-time around each string is unusual, not curved in the ordinary sense, but conical, like a sheet of paper with a narrow wedge removed and the edges pressed together. When two such conical geometries overlap, when two strings pass close enough to each other, the mathematics produces something strange. A region forms between them where the paths through space-time loop back on themselves, closed time-like curves, the same structures that appear inside rotating black holes and in Gödel's rotating universe. A region, in other words, where, if you could navigate it, you might return to your own past. Gott's result was mathematically careful. It did not require exotic matter. It did not require a wormhole. It required only two cosmic strings, moving fast enough, passing close enough. And yet, no cosmic string has ever been directly observed. We have looked. Certain patterns in the cosmic microwave background, the faint afterglow of the early universe, might carry the signature of a string's gravitational influence. Some surveys of distant galaxies have searched for the subtle lensing effect a string would produce, doubling the image of whatever lies behind it. So far, nothing conclusive. Observations have placed upper limits on how dense a network of cosmic strings could be without us having noticed. But whether any exist at all remains, as far as we can tell, an open question. The universe may contain these ancient seams, or it may not. The mathematics permits them. The observations neither confirm nor rule them out, and so they remain in that quiet space between possibility and evidence, where so much of the deepest physics lives. There is another boundary worth resting near for a moment. Inside certain black holes, the rotating ones, the charged ones, there is a surface that physicists call the Cauchy horizon. It lies deeper than the outer event horizon, deeper than the region where escape becomes impossible. It is a boundary of a different kind. Beyond the Cauchy horizon, the equations of general relativity lose their ability to predict, not because something violent happens there, necessarily, but because the structure of space-time beyond that surface allows information from the entire future of the outside universe to arrive in a finite moment. The causal order that makes prediction possible begins to dissolve. It is also, in many of the geometries where closed, time-like curves appear, the surface where those curves begin, the Cauchy horizon is, in a sense, the threshold of time travel. The place where the ordinary forward flow of causality gives way to something more tangled. And yet most physicists believe you could never actually reach it. Not because the journey would be too long, but because the horizon itself is likely unstable. Quantum effects, the same restless fluctuations that fill empty space with borrowed energy, that produce the Casimir force between metal plates, would amplify near the Cauchy horizon. Energy would accumulate there, growing without bound as signals from the entire future of the universe piled up at that single surface. The horizon would likely be destroyed by this accumulation before any traveler could cross it. The universe, it seems, has more than one way of protecting its own history. The chronology protection conjecture, the instability of the Cauchy horizon, the enormous energies required to hold a wormhole open, each one a quiet barrier, placed not by any rule that says time travel is forbidden, but by the accumulated weight of how things actually behave when you follow the physics all the way through. And so we arrive, gently, at something more personal. Something that belongs not to black holes or cosmic strings or the early universe, but to you, to any clock, to any object that moves through the world. Proper time. It is the time measured by a clock that travels with you, the time recorded along your specific path through space-time, your world line. Every object traces a world line, a continuous thread through the 4 dimensions of space and time, marking every position at every moment of its existence. And the time elapsed along that thread, the time your own clock would measure if it traveled with you every step of the way, is your proper time. It is, in a sense, the most honest measure of time there is. It does not depend on who is watching. It does not depend on how fast you are moving relative to someone else. It is simply the accumulated tick of a clock that has lived exactly your life, gone exactly where you have gone, moved exactly as you have moved. 2 clocks that begin together, separate, and come back together will almost always show different proper times. Not because one of them malfunctioned, but because they travel different paths through space-time, and different paths accumulate time differently. The geometry of the universe makes this not just possible, but inevitable. The cosmonaut who spent months aboard a space station returned to Earth with a proper time very slightly shorter than the people who had waited for him on the ground. The muon born in the upper atmosphere and racing toward the surface carries a proper time so compressed by its speed that it survives long enough to arrive. Every particle in every accelerator is living out a proper time that runs slower than the clocks in the laboratory watching it. Proper time is not a correction or an approximation. It is the real thing. The time that actually passed for a particular piece of the universe, moving in its particular way through its particular corner of space-time. And your proper time, the time accumulating along your own quiet world line right now, is doing exactly what it always does. Moving forward, slowly, in the stillness of this moment, the breath a little slower than it was, the thoughts a little softer at their edges, the body already somewhere between waking and the other place. Your world line continues, unhurried, carrying you through the geometry of the night. Let it carry you. 2 clocks that begin their lives together, synchronized, ticking in perfect agreement, will not agree when they meet again. If one of them travels, moves through a gravitational field, accelerates and returns, it will have accumulated a different amount of proper time than the one that stayed behind. Not because something went wrong, not because of vibration or temperature or mechanical drift, but because the geometry of the path they each took through space-time was genuinely different. One path was longer in space and shorter in time. The other was shorter in space and longer in time. And the universe keeps an honest account of both. This is not a paradox. It is simply what space-time is. A 4-dimensional geometry in which the route you take determines how much time you live through, just as surely as the route you drive determines how many miles appear on the odometer. 2 roads between the same 2 cities can have different lengths, Two world lines between the same two events can have different proper times. Neither road is wrong, neither clock is broken. They simply went different ways through the same geometry. And this has happened to human beings. Not in thought experiments, not in equations on a blackboard, but to actual people living actual lives, breathing actual air. Sergei Krikalev spent more cumulative time in orbit than almost any other human being. Months aboard space stations, moving at orbital speeds high above the surface of the Earth. His clocks, the biological ones, the atomic ones, all of them, ran at a rate slightly different from the clocks of the people waiting on the ground. The two effects worked against each other in small ways. His altitude slowed the gravitational pull slightly, which would have sped his clock. His orbital speed slowed his clock. The net result, accumulated over all those months, is that Sergei Krikalev is approximately 20 milliseconds younger than he would have been had he never left the ground. 20 milliseconds. It is not long. You could not feel it. You could not notice it in any ordinary way. But it is real. It is measured. It is written into the geometry of the path his world line took through space-time, and it cannot be undone. He returned to Earth having genuinely lived through slightly less time than the people who waited for him. A quiet, undramatic, completely verified instance of time travel, forward by a fraction of a heartbeat, but forward nonetheless. And if human beings can do this, so can particles. High above the Earth, where the upper atmosphere meets the constant rain of cosmic rays streaming in from deep space, collisions produce a particular kind of particle called a muon. A muon is something like a heavy electron, unstable, short-lived. Under ordinary circumstances, a muon decays in about 2 microseconds, 2 millionths of a second, even moving at nearly the speed of light. A particle with that lifespan should travel only about 600 meters before vanishing. But the upper atmosphere is roughly 10 to 15 kilometers above the ground. The muon should not survive the journey. The mathematics of its decay say it cannot. And yet, muons arrive at the surface of the Earth in enormous numbers. They pass through your body right now, several each second, as they have every moment of your life. They make it, not because the physics of their decay is wrong, but because time dilation is right. From the muon's perspective, its internal clock runs at the normal rate, 2 microseconds, and it is gone. But from the perspective of the Earth below, the muon's clock is running slow, dramatically slow, because the muon is moving at a significant fraction of the speed of light. What is 2 microseconds for the muon corresponds to something much longer for the ground, long enough for the muon to cross 15 kilometers and arrive. The muon does not know it is time traveling. It simply decays on schedule, according to its own proper time. But the geometry of its motion through space-time stretches that proper time across a much larger slice of the ground's time, and so it arrives. This was first confirmed in the 1940s, one of the earliest clean experimental verifications that special relativity was not just a mathematical curiosity, but a description of how the universe actually behaves. Particles racing through the sky, surviving longer than they should, because time itself bends around their motion. Every cosmic ray shower happening right now, somewhere above you in the dark, is producing muons that should not reach the ground, and do. The sky is full of quiet proof. And so we arrive, gently, at the edge of the deeper question. Not whether time travel is possible, the universe has already answered that in nanoseconds and milliseconds and muon lifetimes. But what it would mean? What it would mean for a person if you could travel far enough, fast enough, and return, you would come back to a world that had aged more than you had. The people you knew might be older or gone. The city might be different. the language might have shifted in small ways, and you would be the same age you were when you left, carrying memories of a world that no longer quite exists in the form you remember it. Who are you? Then, the question of identity runs quietly beneath all of this. You are, in some sense, the accumulation of your proper time, the experiences laid down along your particular world line. If your world line diverges from everyone else's and then rejoins at a different point, you have not simply moved through space, you have moved through a different slice of time than the people around you. Your past and their past, which were once the same, are now different lengths. Causality, too, becomes delicate. The universe seems to protect itself from certain kinds of loops, from effects that precede their causes, from travelers who return to prevent their own departure. Whether this protection is absolute, whether the chronology protection conjecture holds at every scale, in every geometry, remains an open question, one that sits at the boundary between general relativity and quantum mechanics, where our understanding is still incomplete. And the nature of the self, the sense that there is a continuous you moving through time, may itself be something that time dilation quietly complicates. If time is not universal, if there is no single now shared by all observers, then the self that persists through time is persisting through something more personal, more local, more particular than we usually imagine. Your time is yours. Not shared, not universal, yours. And yet the universe has already shown us something that holds across all of this. Time is not a fixed river. It does not flow at one rate, in one direction, indifferent to the matter and motion around it. It bends near mass. It slows near speed. It pools in the deep gravity wells of neutron stars and black holes. It stretches thin along the world lines of particles moving close to the speed of light. It is a geometry, not a current, a shape, not a force. And we live inside that shape. Every clock on Earth is ticking at a rate slightly different from every other clock, depending on altitude, latitude, local gravitational variation. Every satellite overhead carries corrections built into its software because without them, the geometry of space-time would quietly accumulate into navigational error. Every particle in every accelerator is a small, silent demonstration that time is elastic. This is not strange once you have sat with it long enough. It is simply the nature of things. The breath slowing now, the body heavy and still, the thoughts arriving less often and staying less long. Your world line continues through the quiet geometry of this night, accumulating proper time at the rate your particular corner of space-time allows, unhurried, undisturbed. The universe bends time around mass and motion. And right now, in the stillness, there is very little of either, just the soft accumulation of moments, one after another, carrying you forward. And so the night deepens. The body has grown heavier now, the breath slower, and the mind, if it is still following, follows more gently. There is one more thread worth tracing before sleep takes over entirely. It begins with light. Light travels at roughly 300 million meters per second in a vacuum. That number has a name, c, and it is not simply the speed of a very fast thing. It is something stranger and more fundamental than that. Every measurement ever made, in every laboratory, in every country, at every moment in history, has returned the same value for the speed of light, regardless of how fast the source was moving, regardless of how fast the observer was moving. The light always arrives at c. This is not what we expect from ordinary objects. If a train moves toward you and someone throws a ball from its roof, The ball arrives faster than it would from a stationary train. Speeds add, but light does not behave this way. A beam of light sent from a moving spacecraft arrives at exactly the same speed as a beam sent from a stationary one. Einstein took this seriously. He asked what the universe would have to be like for this to be true. And the answer was spacetime. If the speed of light is constant for all observers, then space and time cannot be fixed and separate. They must flex and trade against each other so that the measurement always comes out the same. Time slows, distances compress, and through all of it, c remains unchanged. This is why c is not simply a speed limit the way a road has a speed limit. It is woven into the structure of causality itself. To travel faster than light would mean arriving somewhere before you left, in at least some reference frames. It would mean effects preceding causes. It would mean the ordered sequence of events, the thing we call time, would unravel. The universe, as far as we can tell, does not permit this. And light itself. Light does not experience the journey at all. It travels along what physicists call null geodesics, paths through space-time, where the interval between departure and arrival is exactly zero. From light's perspective, if such a thing could be said to exist, there is no passage of time, no distance. The emission and the absorption are, in some sense, the same event. A photon leaving a distant star 1,000 years ago and arriving at your eye tonight has, in its own geometry, traveled no time at all. This is not a poetic way of speaking. It is what the mathematics says, quietly and precisely. And so C is not a wall that fast things crash into. It is the seam where space and time are stitched together, the ratio that keeps causality intact, the constant that makes the geometry of space-time coherent. Let that settle. And now, even deeper. Even in the stillness of this room, even in the apparent emptiness between things, the universe is not quiet. Quantum field theory, the framework that describes particles and forces at the smallest scales, tells us that what we call empty space is not truly empty. It is a sea of fields, and those fields are never entirely at rest. The uncertainty principle, one of the foundational results of quantum mechanics, places a limit on how precisely certain pairs of quantities can be known simultaneously. Energy and time are one such pair. This means that even in a region of space with no particles, no light, no matter of any kind, the energy cannot be exactly zero. It fluctuates, constantly, unavoidably. These are called vacuum fluctuations, and they're not theoretical conveniences. They have measurable consequences. One of the most direct demonstrations is the Casimir effect. If two uncharged metal plates are placed very close together in a vacuum, they experience a small but real attractive force. There's nothing between them. No charge, no field deliberately applied, and yet they are drawn together. The reason is that the space between the plates is slightly more constrained than the space outside them. Certain wavelengths of vacuum fluctuation simply do not fit between the plates, so the fluctuations outside are richer, more varied, more energetic than those within, and the imbalance pushes the plates toward each other. This force has been measured. It matches the predictions of quantum field theory with considerable precision. The vacuum is not nothing. It is a structured something, humming at energies too small and too fast for ordinary perception, but real enough to move metal. Physicists call the lowest possible energy state of a quantum field its zero-point energy. Even at absolute zero temperature, even with every thermal vibration removed, the fields retain this irreducible minimum. They cannot be stilled entirely. The uncertainty principle will not allow it. This zero-point energy is one of the deepest puzzles in modern physics. When theorists attempt to calculate how much energy the vacuum should contain, the numbers come out vastly larger than what is observed. This discrepancy between the predicted vacuum energy and the measured cosmological constant is sometimes called the worst prediction in physics, not because the theory is wrong in its structure, but because something is canceling or suppressing that energy in ways not yet understood. The vacuum, it seems, has a hidden architecture, and we are still learning to read it. There is a connection here to the earlier thread about wormholes. The exotic matter that would be needed to hold a traversable wormhole open, matter with negative energy density, is not entirely without precedent. The Casimir effect demonstrates that negative energy densities can exist, at least locally, at least briefly. The gap between that small demonstration and the vast quantities a wormhole would require is enormous. But the principle is not forbidden. The vacuum permits it, in small ways. And perhaps that is the quietest wonder of all of this, that the universe, at its most fundamental level, is not a collection of solid things moving through empty space. It is a collection of fields, overlapping and interacting, never fully at rest, never fully silent. And what we call particles are simply the places where those fields have gathered into stable, localized patterns. You are not moving through emptiness tonight. You are resting within a fabric of fields that extends without interruption to the edge of the observable universe. The space between the atoms of your body and the space between galaxies are the same kind of space, threaded with the same quantum fields, subject to the same gentle, ceaseless fluctuation. The vacuum breathes. Not metaphorically, but in the only way physics knows how to mean anything, measurably, consistently, according to equations that have been tested and confirmed. And through all of it, time continues its quiet geometry, bending near mass, stretching near speed, emerging, perhaps, from the relationships between entangled things rather than flowing on its own. The clocks tick at their various rates. The satellites carry their corrections. The muons fall through the atmosphere, surviving longer than they should because motion has stretched their moment. And here, in the stillness, in the low gravity of a body at rest, in the near silence of a mind releasing its hold on the day, time moves at its gentlest pace. The vacuum hums its inaudible hum beneath everything. The fields are present, as they always are, and the night continues its slow, unhurried accumulation of moments, each one arriving softly, each one passing without effort, carrying you forward, into the quiet, into the dark, into sleep. And still, the night holds. There is something worth resting with before sleep takes the last of your thoughts. Something about the speed of light, not as a rule imposed from outside, but as something woven into the structure of what space and time actually are. Light travels at roughly 300 million meters every second. In the time it takes a human heart to beat once, light has circled the Earth more than 7 times. And yet, for all that, light does not experience the journey. This is the quiet strangeness at the center of it. When something moves through space-time, it moves through both space and time together. A stationary object moves entirely through time. All of its motion is temporal. When it begins to move through space, some of that motion shifts, borrowed from the time dimension and given to the spatial one. The faster it moves through space, the more slowly it moves through time. Light moves through space at the maximum possible rate, which means it moves through time at none. For a photon, there is no journey. There is only departure and arrival, with nothing in between. No duration, no experience of crossing the distance. The spacetime interval along a beam of light is exactly zero. Not small, not negligible. Zero. This is what physicists mean when they say light travels along null geodesics. And it is why nothing with mass can reach that speed. As an object with mass accelerates, it gains energy, but it also, in a sense, gains resistance to further acceleration. The Lorentz factor, the mathematical relationship between speed and time dilation, grows without bound as speed approaches the speed of light. To reach it exactly would require infinite energy. Not a great deal of energy, infinite. So the speed of light is not a barrier in the way a wall is a barrier. It is more like a horizon. The closer you approach it, the more the geometry of space-time itself reshapes around you. Time slows. Lengths contract along the direction of motion. The universe rearranges its proportions to ensure that light, measured by any observer in any state of motion, always arrives at the same speed. This was the thing Einstein understood in 1905 that others had not quite grasped. The speed of light is not fast. It is the rate at which space-time itself is structured. Every observer, no matter how they are moving, measures light at the same value, not because light is special in the way a fast car is special, but because the speed of light is built into the relationship between space and time. It is the conversion factor between them, the constant that makes the geometry of space-time what it is. And causality depends on it. If information could travel faster than light, it could, in certain reference frames, travel backward in time. An effect could precede its cause, the sequence of events that gives the universe its coherent story. This happened, then that would dissolve. The speed of light is, in this sense, the guardian of cause and effect, of the arrow, of the quiet forward motion that carries each moment into the next. And beneath all of this, beneath the photons and the particles and the fields that carry their interactions, there is the vacuum, not emptiness. The vacuum of quantum field theory is not the absence of things. It is the ground state of every field that exists, the lowest possible energy configuration. And even at that lowest state, energy remains. This is zero-point energy, the consequence of a principle that runs through all of quantum mechanics, that position and momentum, energy and time, cannot both be precisely defined at once. Even a field at rest in its lowest state cannot be perfectly still. It fluctuates continuously, spontaneously, not because anything disturbs it, but because perfect stillness would require a precision that quantum mechanics does not permit. These are vacuum fluctuations. Pairs of particles briefly borrowing energy from the vacuum, existing for a moment too short to measure directly, then returning what they borrowed and vanishing. The vacuum is alive with this, not metaphorically, but in the sense that it produces measurable effects. One of them can be held in the mind gently. Two metal plates, placed very close together in a vacuum. The fluctuating fields between them are constrained. Only certain wavelengths fit in the narrow gap. Outside the plates, all wavelengths are present. The pressure from outside is slightly greater than the pressure from within, and so the plates are drawn together by nothing, by the structure of the vacuum itself. This is the Casimir effect. Measured in laboratories, confirmed repeatedly, a force with no source except the geometry of empty space and the restlessness that quantum mechanics requires of every field. The vacuum, it turns out, has texture. It has a kind of hidden architecture. The fields are present everywhere, in every region of space, even where no particles have been detected. They underlie everything. Particles are not small objects moving through empty space. They are excitations of these fields, ripples in something that was already there. The electron is a disturbance in the electron field. The photon is a disturbance in the electromagnetic field, and the fields themselves never disappear. They are the fabric, and the fabric is never quiet. There is also a deeper question that physicists have not fully resolved. The vacuum energy implied by quantum field theory, when calculated naively, is vastly larger than what is observed in the universe. The cosmological constant, the energy density of empty space that drives the universe's accelerating expansion, is real and measured. But it is many orders of magnitude smaller than the theoretical prediction. This discrepancy is one of the largest unsolved problems in physics. It suggests that something cancels most of the vacuum energy, some mechanism not yet understood, leaving only the small residue that shapes the large-scale structure of the cosmos. The vacuum, in other words, may contain far more than we can see. Its structure may be what determines the masses of particles, the strengths of forces, the stability of the universe itself. Some physicists speak of the vacuum as a kind of sea, not of water, but of potential, of fields in their ground state, ready to be disturbed, ready to give rise to everything that exists. And here, in the stillness of this moment, in a room grown dark and quiet, in a body that has stopped its motion through space and given itself entirely to motion through time, the vacuum is present. The fields are here, fluctuating at their inaudible frequencies beneath the floor, within the walls, inside the air that moves so slowly in and out. There is no place where they are not, no moment when they rest. And yet their restlessness is so fine, so far below the threshold of any sense that it registers only as silence, as stillness, as the particular quality of a room at night when everything has settled. The speed of light holds its geometry. The clocks continue their small divergences. The vacuum hums its zero-point hum beneath everything that is. And the mind, loosening now, releasing the last of its held shapes, drifts into the field, into the dark.